Okay, lastly, I would like to discuss one more imitation learning approach that is can be pretty strong, pretty powerful, and this is the generative adversarial imitation learning, or Gail. This is from New Rips 2016. And again, I think as before, we don't assume an interactive demonstrator, only an offline set of demonstrations. Anything specific that we want to say about that? No. Okay. So let's go over the procedure here. So this is very similar to general GAN learning, generative adversarial training, where we train two different networks. One is the discriminator and one is the generator. In our case, the discriminator will need to discriminate between trajectories that are provided by the demonstrator, truly provided by the demonstrator, versus trajectories that are provided by the generator. In our case, this will be the policy that we are training. So we're trying to train a policy that results in trajectories that are similar to the trajectories provided by the demonstrator. And we would like to fool the discriminator to not be able to distinguish between the two, right? And so the discriminator is trained to output 0 if input state action pair is by the demonstrator, else 1. And we train it with a loss which is the log loss in this case specifically, okay? So we do supervised learning on the discriminator. We have a set of trajectories provided by the generator, and these grow over time, and we have a set of samples from the demonstrator, right? And we also have all of these samples labeled, right? We know which came from the demonstrator and which came from the generator. Next, the policy, our generator right here, is trained using the policy gradient theorem, right? That is the gradient of J, or we're trying to approximate the gradient in J, where this equals Q times grad log pi, right? When we went over that before. In imitation learning, however, there is no reward function, and consequently there's no Q values, right? Instead of attempting to maximize the Q values, we attempt to fool the discriminator. That is, to maximize the loss of capital D. So capital D here represents the discriminator in the paper and not the demonstration set. Okay, not to be confused. Apologies about that. Okay, so we would like to fool capital D, which is the network here, for any of our state action pairs. Meaning that what we get is that the policy gradient is now the log probability, again we were using the log loss, the log probability of the discriminators, the discriminator multiplied by the grad log pi, right? This is the main idea behind Gail, generative adversarial imitation learning. This is the pseudocode. Some practical notes here is that in this line where we train the policy, age here is not for entropy. Again, sorry for the abuse of notation. This is just from the paper though. This age specifically is the Hessian matrix, because the original Gail paper uses TRPO, natural gradient algorithm, which also uses this term. If you remember, we discussed it before. But you can swap that. You don't necessarily need the TRPO algorithm, and you can actually use different type of expression here, okay, which doesn't require you to use the Hessian matrix. For instance, you can use PPO notation, right, just clipping. And another thing to note is that the Q value is not the action value, but the discriminator loss, right? So again, sorry for the abuse of notation, but as I said earlier, there are no Q values in imitation learning, so this is just the discriminators lost in this paper. Okay, and as we said before, D is not the
Demonstrate.
demonstrator set. This is the discriminator network.